Hey there, it's Shannon Math Chick Myers, and today we are starting our grand journey of Calculus 3. I'm using the Larson and Edwards 10th edition, and let's get going. So the first section, 11.1, covers vectors in the plane, and our goals here are we want to be able to write the component form of the vector, a vector, perform vector operations and interpret the results geometrically, write a vector as a linear combo of standard unit vectors, and use vectors to solve problems involving force or velocities. Yes, I have dogs. Sorry. So why don't you go up, pause the movie, and warm it up a little bit by using your basic algebra skills to find the distance between the points 2, 1, and 4, 7. Ready? On your mark and set, go! You can do it. All right, let's see how you did. If you recall, the distance formula is distance equals, the square root of x2 minus x1 squared plus y2 minus y1 squared, that quantity. And so it doesn't matter which point you use first as long as you keep them in the same order. So our distance will end up being, let's see, if we have this be x1, y1, and x2, y2, we will have 4 minus 2, the quantity squared, plus 7, minus 1, the quantity squared. And then, of course, we'll get the distance will be the square root of 2 squared, which is 4, and then plus 6 squared, which is 36. That's going to take us to distance equals square root of 40. And reducing that root, if you recall, that's 4 times 10. Square root of 4 is 2. So you get 2 root 10, and then whatever units you're in. And in their linear units. Cool, cool? All right. So now, next up, we've got, what's a scalar quantity? What do you think? Well, what you've probably been calling a constant. Let's define this a little bit more. A scalar quantity is a single real number scaled to the appropriate unit. All right, so give examples of quantities which could be characterized by some scalar. What do you think? Good. Distance, right? You could go twice the distance as you went a different day. So distance is one. What else do you think? Awesome. Volume. How about time? Yep, time could work. These are just some examples. Weight. All right. Now, what is a vector? You remember what a vector is, or you might not have ever learned about them, and that's okay. A vector is beautiful. It's just a directed line segment. So we all know what a line segment is. So a vector is a directed line segment. So it not only has a length or magnitude, it has a direction to it. And so aren't you so excited you're going to get to use trigonometry? Okay, so give examples of quantities which are represented by vectors. Well, 3D orientations, right? What about when you're flying a plane, right? When you're flying a plane, you would use that. Let's see, force. Acceleration. velocity, and many more. So now, like I said, how would you find the length, also known as the magnitude, also known as the norm of a vector? I often end up saying magnitude. I think in linear algebra, they typically say length or norm. So basically, it's just your distance formula is one way to think about it. You're looking at distance. And we'll be looking at, a little bit of a stricter way of looking at it by using right triangle trig, basically. All right, but the distance formula relates to all of them. What makes two vectors equivalent? Well, we'd want them to be, because they're a line segment, right? So the line segment part of it is we would want them to be the same length, right? And they're directed segments, right? So we would want them to also have the same direction, right? Which means they would have the same slope as well. Does that make sense? Awesome. All right, well, let's keep going. Now let's take a look at the definition of the component form of a vector in the plane. If V, now notice the notation. There's a special bold notation for vector. If we can't do that, right, when we're writing. So the way we do this is V with an arrow over it. Are we good there? Good. All right, so if V is a vector in the plane whose initial point is the origin and whose terminal point is V1, V2, then the component form of V is given by this vector V is equal to, now your author in this book uses this format. So now V1 and V2, and this is in R2, by the way, is those are real numbers. Now, your author uses these triangle ends, right? Now, you could also write a vector if you're also taking linear algebra. I'll just say for our linear algebra book, the notation is going to be the vector V would equal to, we just use parentheses, V1 and V2, because this other notation would represent an inner product. But I just wanted to let you know a lot of times people are taking both of the classes at once, right? So the coordinates V1 and V2 are called the components of V. And if both the initial point and the terminal point lie at the origin, then V is called the zero vector, and it's denoted by that bold 0 or 0 with an arrow over it. Good so far? Now, one thing I'd like to make note of before we go on to our first example, let me think, we should have plenty of room right here. So if you have some point P, call it P1, P2, we're just being R2, is the initial point. And Q, this point Q, call it Q1, Q2, is the terminal point. Then you want to make some vector V, right? So this vector v in component form is simply v equals q1 minus p1, comma, q2 minus p2. Good so far? All right, so keep that in mind for our example. Let's name our axes. We've got x and y. I think if we do our scale of just 1 for each box, it's 7 to negative 7. So let's draw a picture of this. So our example calls on us to sketch the vector whose initial point is the origin and whose terminal point is 3, negative 2. So initial point, the origin, that's easy enough. And then 3, negative 2, we'd have 1, 2, 3, and then down 2. And then making our directed segment there, that's our vector v. Now, what is vector v in component form? Well, our vector v is right here. And writing vector v in component form, we would have v is equal to, what would our q1 be? Beautiful. We'd have 3 minus 0, comma, negative 2 minus 0. Sorry, I've been teaching linear, so I'm used to just putting regular parentheses. So then v would equal to 3, negative 2. Cool, cool? All right. So there we have it. Our first vector, we sketched it and put it in component form. Woohoo! Let's move along. Definitions of vector addition and scalar multiplication. So what we have here, we've got vector u is equal to u1, u2, where those are scalars, and that's in component form. And vector v is v1, v2. These are vectors, and c is another scalar. So I guess we should say u1 and u2 are the real numbers, and the real numbers for right now. So it turns out that the vector sum, so if you're adding vectors, of u and v is the vector u plus v, which is in component form u1 plus v1, comma, u2 plus v2. Good so far? Awesome. The scalar multiple of c and u is the vector c times u. Don't forget to put your little arrow over the vector u. And then that c scales both of these. So we'll have, c times u is going to be c times u1, comma, c times u2. The negative of v is the vector negative 1 times v, or the opposite of v, and that's going to end up being negative v1, negative v2. And the difference of u and v is the vector u minus v, but we don't have subtraction defined. Just like in real numbers, we define subtraction as adding the negative or adding the opposite. So u plus negative v and that is going to equal to, well, at the end of the day, what are we going to get? u1 minus v1, comma, u2 minus v2. Okay, so moving right along, our next example, let's find the component form and length of the vector v that has an initial point of negative 1, 4 and terminal point 7, 3. And let's also find the norm or the length of v. So if you want, go ahead and pause the movie and try this one on your own. Otherwise, you can work it with me. Ready? On your mark and set, go. Give it a try. I know you can do it. Woohoo! Okay, let's see how you did. Well, V is equal to, what did we say in general? So V has some initial point, -1, 4, and a terminal point of 7, 3, right? So remember in general, what did we say? V was equal to Q1 minus P1, comma, Q2 minus P2. So if we call, and if you also recall, our initial point we called P, right? So this one here would be P, and this guy here, the terminal point, would be our Q. Cool so far? So, well, V would equal to, our Q1 is going to be 7, and our P1 is -1. And then Q2 is 3, and minus P2 is 4. Cool so far? All right, so V then would equal to 8 and -1. How'd you do? Awesome. So this is the component form. So right here, what did they ask us to find? So the component form of V is this right here. And now what do we need to find? We need to find the length of V, right? So the length of V is going to be, what do you think? Well, didn't we say we could just use the distance formula, right? The distance formula. So if you use the difference formula on P and Q, so we're going to play around a little bit here, and you might have done this directly, and that's fine. But the distance between this P and Q, right, wouldn't that be the square root of 7 minus -1 squared plus 3 minus 4 squared, which would give us the square root of, what is that, 8 squared plus -1 squared. Good so far? Which would be root 65. What do you think? But look at that. Didn't you do half that work already when you were finding the component form? So what's really super awesome is that this is also equal to the magnitude of V, which is denoted like this. And it turns out that the magnitude of V ends up being the square root of the first component squared plus the second component squared. So if you get it into component form, which we did, then when we find our magnitude, we're already home, right? So the magnitude of V is going to equal to the square root of 8 squared plus -1 squared, and we already found that to be root 65, and that's in linear units. Cool, cool? All right, so our answer for our magnitude then, our length, is 65 units, and this is the notation and formula. Groovy? All right, let's keep it going. So now our next example, example 3, we've got these two vectors. So let's just take a look geometrically at what we have going on. So in our first one, we've got U and V, and we want to be able to kind of draw these guys out, and we want to be able to see geometrically what's happening and then change it into a shortcut algebraically. Good so far? So if we do this geometrically, let's see, we've got to be able to have 8 below. So that's 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So this goes down to -8. This goes 1, 2, 3, 4, 5, 6, 7, 8. I think they're all 8s. I wonder if my last one were 8s. Uh-oh. I'm not even going to look. So here we go. We've got our scale and call it X and Y. All right, so let's go ahead and draw out our vectors. So why don't we'll let U be in blue. So U is -1, -3. So basically from the origin, you just plot that point. -1 and then 1, 2, 3, -3. Draw your arrow. And that's our vector U. Cool, cool. And that has that terminal point of -1, -3. Now the vector V, we'll do in purple, and that's 2, -8. So 2, -8. So we're down here. And that's our vector V. So we want to do U minus V. But remember that U minus V, that's equal to U plus -V, the opposite of V in the vectors. So let's do this. Let's go ahead and do the opposite of V. I guess I'll do that in a little different color. The opposite of V is going to be 2 to the left and then 1 and then 8 up. Right, so that's our -V. Now, when you're adding, what happens is you end up making a parallelogram. Gotten our picture going, right? So now let's do this kind of dashed blue one, and it's going to be, let's attach it to the terminal point of -V. And so that would be -1, so 1 to the left from the terminal point, and then 1, 2, 3 down, right? So this here. And then you end up making this little parallelogram. Like that, right? And here's the beauty of it. Oh goodness. The terminal point from the terminal point as you go from initial point of the origin to this here is what that vector is going to be. And so if we kind of zoom it in, we're going to be at 1, 2, 3 to the left and 1, 2, 3, 4, 5 up. So the vector U minus V is equal to, what did we say, -3 and 5. Now, algebraically, well, what could have happened? I mean, what do you think you might be doing? So if you do U plus -V, wouldn't that equal to -1, -3 plus, what's -V going to be? Good, -2, +8. And then that gets us -1 plus -2, comma, -3 plus 8. And that gets us -3, 5. Okay, so we've got a picture of this, and we've got how you would do it, how you're going to do it most of the time is just this algebraic way. Good so far? Awesome. All right, so -2 times V means what? We're going to scale we're going to scale v by -2, all right? So it's going to flip, right, and then double in length. So let's check it out. We're going to have to change the scale on this, I think. So we can keep this one the same. So this would be 8 and -8 for the horizontal. And then for the vertical, we'd have to go to 16 and -16. So again, if we draw V, what do we draw V in initially? Purple. We were at 2, -8. So we'd be at 2 and then 2, 4, 6, -8. And so here we are. That is V. Well, we've already flipped V, haven't we? And we flipped V using this color. And so that ends up being here, 2 to the left and then 2, 4, 6, 8 up. So this here is V, right? But what do we need to do with V? We need to double it. So we need to add another V, right? So 2 and then 2, 4, 6, 8. We're adding on another V to the terminal point of -V. And so where do we end up? What's our terminal point? This terminal point is at -4, 16. Cool? So -2 times V, the way we worked it out geometrically was we doubled -V. So we ended up getting -4, 16. Now, if we were to do this algebraically, -2 times V would be -2 times, what was V initially? 2, -8, so that's a negative sign. 2, -8. And that in turn would be -4, 16. Cool? All right, so there we go. We are done with this example. Everybody doing okay? Awesome. All right, next up, theorem, properties of vector operations. All right, so here we go. U plus V, this we already showed geometrically, right? It turns out that U plus V, well, it's also equal to V plus U. So these are all the addition properties, okay? And these are all the scalar multiplication properties. So this one, it turns out that we've got commutativity under addition, commutative, and then quantity U plus V plus W is equal to U plus quantity V plus W. Very good. And that is what property? Beautiful, the associative property. And some vector U plus the 0 vector is just going to be U. So what property do you think that is? Beautiful, additive identity. And then U plus -U yields the 0 vector, and so that's our additive inverse. All right, cool. So under these multiplication ones, the scalar C times the scalar D times vector U would also be equal to C times D times the vector U, and that is associative. The sum of C plus D times the vector U is equal to C times U plus D times U. That is distributive. And so is this one, right? C times the sum of these two vectors, U and V, is going to be C times U plus C times V. And so that is also distributive. And the last one, it turns out, is 1 times the vector U is equal to the vector U. And the scalar 0 times the vector U yields a vector, which is the 0 vector. Cool so far? Okay, so now, I don't know, we can do a little proof of one of them. I don't know if we have any preferences here. Why don't we just do commutativity? So we'll do the proof of a number for number 1. So, and you'll probably see all these proofs in linear algebra too. So here we go. If we need 2 vectors, right? And we're doing these are vector operations in the plane. So we're going to let U equal to U1, U2, and V equal to V1, V2, such that, that's what that means, such that U1, U2, V1, and V2 are elements of the real numbers. And so now we start out with our premise. Our premise is U plus V, and we want to show that it's commutative. So U plus V, if we put them into component form, is going to be what? Beautiful. U1, U2 plus V1, V2. That's just putting them in component form. Now, by definition of vector addition, what do we have? This is going to be U1 plus V1, comma, U2 plus V2. And that's by definition of vector addition. And then, continuing, that's going to equal to, well, what about the real numbers? Don't we already know all this stuff about the real numbers? Aren't they commutative? So we can say this is equal to V1 plus U1, comma, V2 plus U2, and that's because this set of real numbers is commutative. And then, finally, well, what is that? Well, not finally, we got 2 more steps. We got V1, V2, plus U1, U2, and that's, again, by definition of vector addition, going the other way. And then, finally, what is that? That is equal to the vector V. You know what, I'm going to bring this over here so it's not smushed. So that is equal to the vector V plus the vector U, which is what we wanted to show. Groovy? All right. So next up, we have the theorem, the length of a scalar multiple. So let V be a scalar, let V be a vector, and let C be a scalar. Then it turns out that the magnitude of C times V is equal to the absolute value of C times the magnitude of V. Cool so far? And here we go. Another theorem. Unit vector in the direction of V. If V is a non-zero vector in the plane, then the vector U equal to the vector V over the magnitude of vector V has length 1 and the same direction as V, which is very, very useful, all right? So, for example 4, find a unit vector in the direction of this vector V, and then verify it has length 1. So, okay, here we go. Well, V is equal to 7, negative 5, right? And so the magnitude of V, remember, is beautiful. The square root of 7 squared plus negative 5 squared. Well, that's going to equal to the square root of, what is it, 49 plus 25, which is equal to, what is that, root 74? 74? So, U equal to V divided by the magnitude of V is going to equal to 7, negative 5 over the square root of 74. And then oftentimes what they'll do is they'll bring it into the radical. I don't care about you rationalizing denominators, by the way. So we'll bring it into we'll bring the scalar, which is 1 over root 74, into the component form. So we'll get 7 over root 74, comma, negative 5 over root 74, and we're done. Now, if you want to verify that this has that U, what the magnitude of U is, and that it has a magnitude of 1, what do we do? So verifying, we'll have so the magnitude of U is going to equal to the square root of 7 over root 74 squared plus negative 5 over root 74 squared. So the magnitude of U will be 49 over 74 plus 25 over 74 under a radical. So we'll get the magnitude of U is equal to, what's that, 74 over 74, which is root 1. So length is positive, and actually we have a scalar in there anyway, so it's the absolute value of 1, so we get 1. So check, we're done. Good, good? All right. Now let's talk about standard unit vectors, okay? So, and this is in the plane. So the I vector is, in component form is 1, 0, and J vector is 0, 1, okay? So if you have, I want to see a picture of it, it's just going to be, let's call this 1 right here so we can see it. So the I vector would be this one here. And the j vector would be the one that lies along the y-axis and has a length of 1. Cool, cool? So this is j, and this one was I. Okay, so the cool thing about using these, is that you can simplify a lot of things. So for example, if you have something like 2 times I, right? That's just going to be 2 times the vector 1, 0, which of course is 2, 0. So that means that you've just scaled the vector I by 2. Does that make sense? So here, if you kind of think about this in general, if you've got some v equal to v1, v2, then couldn't we write this as v1, let me do a different line, sorry. We could definitely write this as v1 times the vector 1, 0, couldn't we? Plus v2 times the vector 0, 1. And what is that? Awesome. It's v1 times I plus v2 times j. Cool, cool? And actually, I think a lot of times people write them more with the hat on them instead of the arrow. So you might be seeing them v1 times I, like that, plus v2 times j. All right. So let's look at our next example, example 5. Let u be the vector with initial point, -4, 1, and terminal point, 3, -1. And let v equal to 5i plus 2j. Write each vector as a linear combination of I and j. Okay, so what do we have to do for u? U is going to equal to what? Beautiful. U is going to equal to the terminal, remember the terminal minus the initial, so we'd end up having 3 minus -4, comma, -1 minus 1. And so u equals 7, -2. And so that's like your u1, u2. So now we can just write that as u equals, beautiful, 7i minus 2j. Awesome. Okay, so let's look at B. W, the vector W, is equal to 4 times u minus 2 times v. Well, what did we find that u was equal to? Beautiful, 7i minus 2j. And then we have this minus 2 times v, and v is equal to, it was given already, as 5i plus 2j. So this was v, and then this one was u from what we found last time. So our vector w then, when we bring that 4 in, we'll get 28i minus 8i, or 8j, my bad, minus 10i minus 4j. So w will equal to 18 i's minus 12 j's. Good so far? Awesome. All right, so example 6. Again, if you want to try any of these on your own, you're good. This is our last example for this lecture. So the vector v has a magnitude of 2 and makes an angle of pi over 3 with the positive x-axis. Write v as a linear combo of the unit vectors I and j. Okay, well, let's check it out. And again, if you want to try this on your own, feel free. Pause the movie. You can do it. You're awesome. Okay, let's see how you did. I'll let this be 1. And if we make our circle here, oh, I love technology. Isn't that cool? Awesome. Perfect. So we've got our unit circle going on, and this would just be our x and our y, right? So let's draw our vector here. So our vector, what do we get? U. We know it has a magnitude of 2, right? So our vector 2 has a magnitude of 2, and it, well, I'm sorry, our vector v. Let's start with a vector u that's on the unit circle. So pi over 3, theta is pi over 3. So you're going to have something like this, because we want the same. So this would be theta equals pi over 3. This is going to be 1. And this ordered pair, remember, is cosine theta sine theta. And that would be our u1 and u2. So let's find v, right? So the main difference, because remember that we've got to have the same slope, which means the same angle with the positive x-axis. So all we need to do now is we need to find the components we need and double them. So what do we know? We know the magnitude of v is 2, right? So the magnitude of v is 2. That is given. We also know that u is equal to u1, u2. Good so far? But we also know that what was u1? It was cosine theta, but what was theta? Pi over 3. Beautiful. So we're going to have cosine pi over 3 and then sine pi over 3. Okay. So what is that? Well, u is cosine pi over 3. You should know this without looking, is beautiful, 1/2. And then sine of pi over 3 is square root of 3 over 2. So here what we've orchestrated this to be is that u is equal to v over the magnitude of v. But in this case, we know what u is, right? So if we isolate v, which is what we're looking for, that would be equal to what? The magnitude of v times the vector u. So v would be 2, because that's the magnitude of v, and then the vector u is what? 1/2 root 3 over 2. So multiplying the 2 through, we get v is 2 comma root 3. And then what? Putting that in terms of I and j, v would be 2i plus root 3j. Groovy, huh? All right, that's it, and that's it for this lesson. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe and tell your friends. All right, bye.